Okay, thank you very much, Tom and Yash, for the nice invitation. So my goal today is to talk about some recent work on the Euler equation, and I just want to mention some small facts about the Euler equation. So it describes the motion of an ideal fluid, and today we're not going to think much about boundaries, so U is a velocity field. And P is a pressure field. And the sole purpose of the pressure here is to enforce the second condition. So this enforces the divergence of U is 0. Okay, and this is called the incompressibility constraint. Okay, so what incompressibility means is that you can't squeeze fluid into small regions, and this is seen as sort of like a deterrent to singularity formation. Okay, so what are some facts we have about Euler flows? The first fact is energy conservation. So this is true for all time, so long as the solution is regular, right? So if U is nice enough. I think you've heard about this issue a lot in recent years. Second fact is that forgetting about decay assumptions, so forgetting decay assumptions, you have the following a priori bounds. So if U is a solution, if U in C1 alpha space-time solves the Euler equation, you have the following kind of bound. ddt of U in C1 alpha is bounded by a constant divided by alpha. So this is a dimensional constant. Okay, so this is a well-known computation, and I think in some form or another this goes back a long time. So maybe to some of the earliest works on the Euler equation. Okay, and a consequence of this a priori bound is that you have local well-posedness, so local existence and uniqueness of C1 alpha solutions. Okay. Okay. And the question is, which one could ask? So, question: is it possible that a solution U, which is C1 alpha in space-time on R3 cross 0t, 0 to 1, say, becomes singular as t goes to 1? Singular as t goes to 1. Okay, so 1 obviously is just an arbitrary number which can be made anything by scaling. So this is the finite time singularity question. Um, okay, one thing which is known, so I'm not talking much about the decay, but one should really care about like finite energy solutions. Okay, because it's known already, even if you have C infinity solutions, for which the velocity and its gradient grow linearly at infinity, then you could have singularity formation. Okay, so one thing which is known is that it's not a question. One thing which is known is that singularity if and only if the vorticity becomes infinite in finite time, pointwise. So what is that? So it's in 3 dimensions. It's very useful to introduce the vorticity. So that's the curl of the velocity field. And basically you have singularity as t goes to 1 if and only if the limit as t goes to 1 of this integral is plus infinity. Okay, so this is the so-called Beal-Kato-Maida criteria. All right. So a consequence of this. So one could also ask the same question about smooth solutions. Okay, so same question. Okay. And okay, so my goal today is to discuss a negative answer to the first question. Second question, I think, is.
You mean a positive answer?
Oh yeah, a positive answer to the first question. Right. Thank you. Positive answer to the first question. The second question, I think, is on the whole space. Basically, nobody knows. I think it's not even clear what the answer is. Okay, so let me just state the theorem.
Do you need to work in R3 or can you work in some other kind of geometry?
Yeah, it's very likely that you can work in periodic or any other kind of geometry. Okay, but yeah, it's likely. I'm not going to say it is, but it's very likely. So let's state the theorem. So theorem. So there exists an alpha positive. So alpha is astronomically small, and U0 in C1 alpha of R3. And an important condition is that the gradient of U0 decays at infinity. So as I'm stating it, the data does not have to have finite energy, but it does have to satisfy this decay condition. Yeah, sorry. Okay, let me just put it there. So that the unique local solution starting at U0 satisfies that. So the limit as time goes to 1 of this integral is plus infinity. Okay. So one remark is that the type of solution we're talking about has a very simple form in space-time. So the solution can be written as some self-similar in a self-similar way. So it's like okay, and beta is a very large number. So beta is alpha is very small. Beta is approximately 1 over alpha. Okay. Is there any question about the statement? Or
Yeah. So
yes, sir.
the x is f. So x is going to be rotation. It's going to be absolute value of x, or
No, it's just x.
okay. And
So you just scale each.
Where's the magnet not smooth?
Right. That's a good question. So where is basically f? So f is a C alpha function, and it's not smooth. So let me try to. It's not smooth on this plane, z equals 0. It's also not smooth. I do not believe that the lack of smoothness on the plane is necessary. The lack of smoothness on the axis for this construction is necessary. But otherwise, it's C infinity.
And it's C alpha.
And it's globally C alpha. Okay, so how does the construction go? Okay, so the construction is based, I think, on four main ideas. So I'm going to try my best to explain all of them. So there's first idea is how you understand the relation between the vorticity and the velocity, right? So you have a map called the Biot-Savart law, which sends the vorticity. So vorticity, remember, is the curl of u, and the divergence of u is 0. Okay, it means that if you take the curl of this equation, you get minus Laplace of u is curl of omega, which means you can recover u from omega, right? So omega gives Laplace u, which is minus Laplace inverse of the curl of omega. And there's an extra gradient outside. Okay, so one of the main ideas is to write this operator, so this is a 0th order operator, as what I would say like a singular part, which you can understand very well, and a regular part, which you don't really care about. Okay, so this is like a decomposition. Right. So this is motivated by a work of Kiselev and Schwerak. Right. So it's that's really the origin of all of this. The second main tool is to study, basically to understand how equations like this work. Okay, so I didn't write it, but the vorticity equation has the following form. So the vorticity equation has the form dt of omega plus u dot grad omega is omega dot grad u. Okay, so this is like a one-dimensional version of that. So we have to try to get an understanding of how these two terms interact with each other. Okay. A third part is to talk about self-similarity and stability. Right? So if you have, for some equation, like a self-similar blow-up, how do you prove that like a nearby equation or nearby solutions will also blow up, right? So this is like a general thing. And okay, so once we know what these are, we'll know what the fourth is. So this is, we have to study this, finally, this model equation. Okay, and so I hope that to talk about a little bit about each. Okay, so let's start with the first one. So this is understanding the map omega goes to grad u. Okay, and basically the idea is that it's well known that the operator d2 Laplace minus 1 is unbounded on L infinity. Right? It's not a bounded operator. And furthermore, one consequence of this, or one sign of this, is that when you consider this operator on C alpha spaces, so again, forgetting about decay considerations. So when you think about the operator norm, you get something like that, which at alpha equals 0 is basically this statement. Okay, so now we want to understand in a sufficiently deep way this the nature of this fact. Okay, and what this is based on is that for this fact, there are essentially two counterexamples, or one counterexample, right? Basically, you just consider the following function: psi is xy log x squared plus y squared multiplied by a cutoff function, if you want. And then this function satisfies that Laplace of psi is bounded, right? But d2 of psi is unbounded. Right? And this kind of example you can come up with in any dimension. Okay? But surprisingly, it's almost the only example. Okay, so so when I say only example, I mean the only well-behaved example. Okay, so what's the theorem? Okay, so theorem. So we have two parameters, alpha and s is some integer. Okay, so let's assume that capital F is HS. So now I'm thinking about a function of a radial variable and an angular variable. And I also assume
But S1 or S2 or some other.
there's two dimensions. So I'm thinking about in two dimensions. So yeah, and this example is two-dimensional also. So sorry. Okay, so let's assume that f is some function in HS. Now, if you consider d2 of sorry. Also assume that the integral on S1 of f of r theta e to the I n theta d theta is identically 0 for n equals 0, 1, and 2. Okay, so you make this assumption. Okay, and now we want to understand what is d2 Laplace inverse of a function of r to the alpha and theta. So now you want to think f is a super nice function. Its argument r to the alpha is not very nice, okay, but we know what it is, and we want to understand what is this, okay. Yeah, an example of this would be so an example of this kind of function would be something like xy over x squared plus y squared to the 1 minus alpha, something like that. So it's a Holder continuous function of degree alpha, and sort of approximates this example, right? So this would be like the Laplacian of psi. Okay. Okay, sorry. Okay, so we consider this and we call it some function g of r to the alpha and theta. Okay, then the statement is that g in HS is bounded by f in HS. So g. So then and this CS is independent of alpha. Okay. So no matter how sort of irregular it is in the R variable, as long as you have this orthogonality condition, the operator d2 Laplace inverse is bounded, independent of alpha. Okay. So in particular, if you think about this example, this is the function in coordinates sine of 2 theta r to the alpha, right? So this it doesn't apply to this one, right? So the statement doesn't apply to that. So this is the first part. Second part of the theorem is if you do not have that orthogonality condition, so theorem part 2, if no orthogonality condition, then g can be written as g1 plus g2. This is a radial function, and okay, it's actually 1 over alpha times radial function which just depends on the inner product of f with e to the 2i theta on S1. Okay, so the point is that it's radial and has a very nice form. And it's what contains all of the singular part. Okay, so this is the reason for basically the lack of, so this 1 over alpha in the Schauder estimates is coming in this setting solely from this guy, this coefficient.
G2 is bounded.
All right, yeah. Yeah, sorry. And G2 is bounded. Yeah. Right. So this gives you a decomposition of the gradient of the velocity into a very nice singular part, which you know what it is basically. So some like one-dimensional piece. And then another part which is, you consider it lower order. Okay? And okay, the proof of this fact is not very difficult. So this is so that just to give a idea of what I'm saying. So basically what I'm saying is that if you take the Laplace inverse of sine of 2 theta r to the alpha, okay, let's just put some cutoff, right? This will be something of order 1 over alpha times radial plus order 1. I'm thinking of alpha as a small parameter. But on the other hand, if I took this guy, this is just order 1. Okay? So this kind of thing we have to basically differentiate.
This is a two-dimensional Laplace in here as well.
Correct. Correct. So this is like the xy. But there are versions in 3 dimensions and higher. Okay, so this all has to do. So the point is that sine of 2 theta r squared is the harmonic function. That's the only thing which is behind this. Okay, so that's the first part. Okay, so from there already we can tell that okay, if we write this equation.
Is the same true with Holder spaces with Bayes?
No, that's a good question. So if you just think about Holder spaces, you can't make this decomposition. Right? If you think, just forget about this thing, just say R and think of f as a C alpha function, you can't make this statement. Right. Okay, so now from there you think, okay, u can be written as something like, or gradient u can be written as something like 1 over alpha times some operator of omega. So I'll just write it like that. Plus order of 1. Okay, so this is like a singular part and regular part. And then you plug it in the equation and drop the regular part. Okay, so then you make like an approximation and set this equal and see what happens. Okay. Okay. So we'll do that a little bit later. Okay. Second part. So part 2 now. So this is all just to give a nice form to this. So basically what we're going to say is that you can write this like this, and then this is a radial function, and okay, now this nonlinearity is easier to deal with. Okay, but we still have our transport term. So now I want to talk about how you can deal with that. Okay, so okay, so it's been known for a while, at least from work of Peter and others, that basically if you take the Euler equation and you cancel this term, then the equation you get should have like singularity in finite time. Okay, so the transport term is a sort of a deterrent to singularity. Okay, so the idea, so the philosophical idea is that this term, which is called the vortex stretching, okay, so vortex stretching leads to growth, okay, and transport sort of stops the growth in whatever way it does. Right, this is just
Nonlinearity is the nice word to say.
okay. Yeah, depletes this growth maybe. Okay. So you should look for scenarios. So that means that you should look for a scenario which favors the right-hand side, which favors the vortex stretching. Okay, that's basically the idea. People do this in different ways. So, one way recently there was some numerics by Tom Howe and Guo Luo on singularity formation in domain with boundaries, and that's I think very clearly the reason for the boundary is to deplete this guy. Right. So let me explain what's going on. So it's good to look at a model. Right, so model. Okay, so this I think is an interesting model. So you can either you set this on an interval or on the circle. Okay, so this can be on 0 to pi or on minus pi to pi with periodic boundary conditions. Okay, so if you go on 0 to pi, then you solve this equation by putting Dirichlet conditions on U. Okay. Okay, so what's funny about this model is that you have global regularity.
Are you thinking omega and U is being scalars here or not?
Yes, yes, this is just a scalar problem, one-dimensional, simple. Here you have global regularity if the solution is smooth enough, so omega 0 is C2. But you have singularity in finite time if the initial vorticity is just C alpha for alpha less than 1. I think the correct threshold is 1. So we can check that sometime. But and finally, you have singularity formation if omega 0 is C infinity on 0 to pi. Right? So when you impose a physical boundary, say at theta equals 0, you can have a singularity. If you take data which is continuous but not C1, you can have a singularity. But if you have C1 data, you have global regularity. So I think it's a very interesting model equation. So this was observed, I think, first by Alejandro Soria and Ralph Saxton. And the idea is the following. Okay, so you're studying this equation. Okay, so to get blow up, you need omega to be going up. So you need dxu to be positive at the point where you think a blow up is going to happen. And so it makes sense to look at data where which looks like this. Okay, here, say you take data which is odd in the x variable and positive over here and negative over here. And then it's easy to see that minus dxxu is omega, means that u has the same shape, right? So u looks something like that. Right? And this makes, so that means that dxu is positive here. Okay? So this should cause growth of omega near the origin. Okay? The problem is that at the same time, you have this term, which is pushing the value of omega equals 0 into the bulk. Okay? And if you exactly have u dx omega and omega dxu, they're exactly balanced and there's no blow up, so long as the vorticity is linear at the origin, okay, initially. Okay, so for example, omega is identically sine x is a stationary solution of this problem. Okay, so it's an exact balance in some functions. On the other hand, if you took data, if omega looked more like this, right, then the effect of the velocity field pushing out is much weaker because almost immediately the vorticity is large, right? So if say the initial data was sine x to the alpha, and alpha is less than 1, I say on the right side, I mean, then you're basically favoring this term, right? And you have a blow up in finite time. Okay, so another way to say it is that if you even for smooth solutions introduce a parameter a here, and if a is very small, then the effect of this is much weaker. Any question? Yeah.
I'm all confused between the difference. One was periodic conditions and the other was Dirichlet. What's the difference between 1 and 3?
Good. That's a good question. So now if you Dirichlet means, so when you solve an elliptic problem in Dirichlet means that you flip to the other side. So basically your data is here, your solution lives here, but when you invert, when you solve this problem, all you do is you make a reflection like that, right? So for data which looks like this, say, data which looks like this, basically it's the same as looking at data on the circle which looks like that. Does that make sense? Okay, what it means is that when you're pushing out vorticity, the vorticity is not vanishing on this boundary. Right? It means you're pushing out positive guide. This is, in fact, just helping the blow up. Right? And that's essentially the effect of the boundary in many of these examples. Any other question? Okay, so the third thing I want to talk about is self-similarity. Okay, now what we're going to do in the end is we're going to start with the Euler equation. Okay, which is, say, this one. Okay, and then we're going to use the information we gained from the first part. Okay, so we say that grad u is basically some piece, some singular piece, plus regular piece. Okay, which means that you can rewrite this equation as dt omega, say, minus 1 over alpha L of omega times omega is equal to the rest. Okay, now the rest is the whole transport term and all of the regular part of u times omega. Okay, so this is an exact calculation, right? There's nothing wrong with that. Okay, and now what we want to see is if you had a blow up for this equation, okay, how can you basically forget about this part? Okay, so in an intuitive way, I explained to you how you forget about the transport term and also how you do this decomposition. But how do you actually prove? So just because this has like 10 million factor in front of it, and all of these have factor 1 or 2 in front of them, it doesn't mean that there's going to be a blow up for this equation, right? So that's now what we want to understand. Okay. Okay, so this is where we go to the self-similarity. So we search for solutions of this form. For the alpha equals 0 problem. Okay, it's not 100% correct to say alpha equals 0 problem, but basically you search for solutions to this equation which are of that form. Okay, now let me just tell you exactly what the equation is. So now we think, so the first we make some reductions. So we're working with axisymmetric solutions without swirl. Okay, which means that we fix the z-axis and we assume that the velocity field is invariant under rotation, basically. So what it means is that u of ox and t is O u of xt for all rotation matrices fixing the z-axis. Okay, so we make this as an assumption. And we further, so that's just the axisymmetric part. The without swirl part means that we also assume that the initial velocity field in the like swirling around the axis is identically 0. And you can check that that's propagated for all time. Okay? And for these, it is correct to think of omega as a scalar. Okay.
You wanted to say different power when we minus t, right?
Say that again.
F.
But this is for the alpha equals 0.
Oh, sorry.
Yeah.
I didn't quite understand what without swirl meant again.
It just means so that the velocity field can be decomposed into 3 parts. So like right, so this is so basically no swirl means u theta is identically 0. So there's no velocity field going around. Okay. All right, then all of these reductions leads us to the following model. So this is the alpha equals 0 model, if you will. So I'm still writing alpha. So alpha equals 0 really means alpha is very small. Okay. And L12 of omega is just integral from r to infinity of omega rho and theta over rho k of theta d theta. Okay, so k is some fixed kernel. Okay, so it's fixed. Okay, it's just sine squared theta times cosine theta. Cosine squared theta times sine theta. But the important thing is that this is a radial function. Okay, and the simple computation tells you that if you're searching for solutions of that form, so you say again. Oh, sorry. Okay, so this is a theta integral. Let me not write the indices. So it's going to be confusing. Yeah, thank you. Okay, and so we're searching for a solution of the form of this form. Okay, and then we play around a little bit, and what we realize is that there are many solutions to that equation of that form. Okay, so there are many solutions. And you can take f to be any function of theta you want times okay, and z is like absolute value of x over 1 minus t. Okay, and gamma is basically any function of theta. So gamma should just these are both functions of theta. They shouldn't be orthogonal. Okay. What's that? Yeah, and this is c. Yeah, thanks. Okay, this is just a calculation, right? So, and it's basically because this is a radial function that gamma in the front comes for free, right? So it's just like if you take as an ansatz omega as a function of theta times a function of z and t. Then the function of z and t will just satisfy some one-dimensional problem, which you can solve. Okay? And so you have these solutions. Okay? And now the question is, so now what we wish to do in the remaining time is, okay, so you search for solutions to the alpha positive problem, which means to the alpha positive problem with omega of x and t is 1 over 1 minus t. So you need to relax the form a little bit. Okay, and with f close to f0, with f equal f0 plus a g which will be much smaller than f0. Okay, that's the approach we follow. Okay, now these two parameters here are there to ensure that certain orthogonality conditions are held. Okay, so let me explain a little bit. Does anybody have a question about the form or the general idea?
So that will solve the full.
This should solve the full equation, right? Yeah. Okay, if not, then I just will explain to you how you do the exact same thing on a simpler problem. And after that, one can just make the necessary adjustments and add a few ideas. But so you consider the following much simpler problem. Okay, so this is maybe too simple, but it's still a problem. So n is some nonlinearity you don't know. So nonlinearity. Okay, it could contain derivatives of f. Could be, quadratic, something like that. So we're just going to assume that everything I'm about to do can be done for that n. So n just is basically like a quadratic thing which could contain transport terms and things like that. So anything which would actually show up. Okay, so then when epsilon is 0, we have the solution of this equation. Then there's a solution. So the spatial and time domain is this one. This is space and time. There's a solution of the form, again, this self-similar form. And now f of z is 1 over 1 plus c. Okay, so you just calculate and you get this.
So can I ask
Yes, sir.
a question going back?
Yeah.
The L is sort of like local in the radial, in the radius direction. So when you look for solutions before, when you're looking for solutions of the form you had before, it doesn't depend, it only depends really on what the values are around when z equals 0.
Well, it is non-local. It's
Not in the z direction, right?
no, it's like this.
So
It's kind of like a Hilbert transform. I forget about the theta dependence, but it's like that. This kind of what L is. S.
rows here.
Yeah.
Ah, okay. So it does.
Yeah. Okay, so I don't know how long I have left. Maybe 1 or 2 minutes. Okay. So so this is the solution, and this is when epsilon is 0. So now you do the same thing, and you again search for a solution of that form. So you again search for a solution of this form. And then for the full problem, you see that capital F, if it has, so this is little f, it should satisfy this equation. Okay, so we have a solution when mu, lambda, and epsilon are 0. Right? Mu and lambda are free parameters. Okay, but we have a solution when epsilon is 0. We just take mu and lambda to be 0 and f to be f0. Okay, so now here we're going to just take it to be our base solution plus g. Try to prove g is very small and exists. Okay, that's the whole thing. And at the end, it's, if I just, if you allow me to write what you get. So if you plug this in, you get the linearization of, we got these linear terms in G, and you get the linearization of this around this guy. So you get L of G. So this is G plus Z dZg minus 2 over 1 plus Zg. Right? So this is your linear operator. Equals a bunch of stuff. Okay? So some bunch of things you get when you plug in this form. Okay? And the point now is that if n was didn't have derivatives in it or anything, you can just think of doing an expansion in epsilon, right? So you just, go to the right-hand side, formally set g equals 0. That will give you, and then you invert L, you get the first term in your expansion, etc. Okay. Problem is that n in what we're looking at contains transport terms. So we need a different way to solve this equation. So it turns out that L satisfies some coercivity estimate. So you can prove that on certain weighted spaces, so they're weighted Sobolev spaces, that this linearized operator is bigger than a fixed constant like that. Okay, and since the right-hand side, this n, does not lose derivatives when you do integration by parts. So when you take an inner product, say of, like if you do something like this, right? Even though this n may have derivatives, usually you just do integration by parts, put the derivative on the velocity, right? So since you have sort of this kind of whatever space you're working on, right? We don't have any trouble from the loss of derivatives. The only problem is that this weighted space is what? So the L2 version is Okay, so in particular, this is the weighted L2 norm. So in particular, for this to work, you need G to vanish quadratically at the origin. In particular, you need the right-hand side. So all these dots here should belong to at least L2W, right? And this is where the free parameters mu and lambda come in. So mu and lambda are chosen so that the right-hand side vanishes to second order at z equals 0. Okay, it's like a very simple caricature. But at the end, if you do that, you prove, because of this coercivity and the fact that n is sort of like transports or normal stretching terms, you get this kind of a priori estimate, so whatever space. Okay. Okay, so you get, oh, sorry. Cubic, sorry. So this can come from like the G squared term, okay? Which then implies that this is less than C times epsilon. Okay, so this is like a simple a priori estimate you get. Okay, to actually prove existence, you should also introduce some time variable here, okay, and then send tau to infinity. It's kind of a simple issue. It's not very complicated to do. Okay, but this is the a priori estimate, and okay, if you work a bit, you can apply this to the Euler equation, like I said. Yeah, I think I'll stop there. Thanks.